Okay, so we almost completed chapter 6, and then we had a review for the midterm, and then you guys wrote midterm on Monday. So today I'll review what we did in chapter 6. I'll try to finish it, and then next week we will have some um, exercises that we will do in Excel and in R. So those are our plans in short. So let us review chapter 6, whatever we did already. Chapter 6 is about multiple linear model. To be more precise, multivariate linear model. This means that we have clearly one dependent variable and more than one independent variables. The model has the following form: yi equals beta 0 plus beta 1 x1i plus beta 2 x2i plus and so on plus beta k x ki plus ui. So this is similar to the bivariate model, where we only have two variables. One is dependent and the other one is independent. But as you see, the difference between multivariate and bivariate models is that we have additional terms that correspond to additional independent variables. Okay, so this ui here, that's the disturbance term. And as you know, we don't know ui. So ui is a disturbance term for observation I, right? Can you guys tell me, so first let me ask you a question. So is this expression a population line? To be more precise, the true population line.
Yes.
Yes, because it's not approximate. It's not from a sample.
So guys, you are partially right, but you are not entirely right. So if you carefully read this question, can you once again think about it and let me know if this expression is the population line? The whole expression. Now, why?
The disturbance.
Exactly. So if you think carefully, you will see that this expression here gives you all of the points in the population, right? And of course, there is a true population line, true line, they call it true population line, that is closest to all of these points. Can you give me the expression of the true population line?
Can I try?
Of course.
yi equals bo plus b1 x1 plus b2 x2 I plus bk xki without a disturbance.
Now you are partially right. Now think about this and try to be absolutely precise. So first of all, you said B's, but I'm sure you meant betas, right? So because those are betas, not B's, right? Betas. So let me ask you, how do you obtain the true, sorry, what I'm writing, true population line? Can you answer this question? Okay, so let me call this expression expression 1. Okay, guys, you see my blue screen, right?
Yes.
So let me call this expression expression 1. How do we obtain the expression for population line? By taking the expectation of both sides of expression 1 and assuming what? Let's say expectation conditional on x. And assuming that the expectation of ui given all of your x's, x1i, x2i, and so on, xki, that is equal to 0, right? And if you take the expectation of this whole thing, of this expression 1, conditional on x, then this is what you obtain on the right-hand side. But what do you obtain on the left-hand side? It's not that, right? It's expectation of yi conditional on all of your x's, x1, I, x2, I, and so on, xki. And we call this the whole thing, we call this the population regression line. Guys, am I clear?
Yes.
So that's what we call the population regression line. But do we know population regression line? We don't know, right? And exactly for that reason, we are trying to get the best possible estimate of the population regression line. And the estimate is the sample line, right? So we don't know the true population line, and we, for this reason, try to obtain the best possible estimate of it. And what do we call it?
Sample.
Exactly. Now, can you give me the expression for the sample line? It will be y I hat equals beta 0 hat plus beta 1 hat times x1I plus beta 2 hat times x2I plus and so on plus beta k hat times xki. So this is our sample line, right? Now let me ask you guys. This is like a review. I'm not explaining anything new, right? So because I want to refresh your minds so that we are ready to move on better from the next week. So why are okay, so beta hat 0, beta hat 1, and so okay. Beta hat 2 and so on, beta hat k, those are estimators for what? Beta 0, beta 1, beta 2, and so on, beta k, right? Now we want to be sure that these beta hats are the best possible estimators. Okay, so when these estimators will be the best possible estimators, what are the requirements that we need to check these beta hats satisfy before we say that they are best possible estimators of the true betas?
Is that it has to be unbiased, consistent, and efficient?
Okay. So unbiased means that the expectation of unbiasedness. Instead, the expectation of beta I, how the beta, let's call it beta J because I is already saved for X, right? So because we have, right? So because above I have yi equals x1I, x2, and so on and so on. So let me call beta J. If the expectation of beta J conditional on all of your x's, equals sorry, beta J, if that's equal to true beta J, where J changes from 1 to what? K, right? Then we say that beta hat J is an unbiased estimator of beta J. But also beta hat J should be consistent and efficient estimator for beta J. Okay, so it is shown that beta hat J, where J changes from 1 to K that are obtained by OLS, ordinary least squares, satisfy these requirements. So which means we are good to go. Can you tell me what does OLS do? It minimizes the sum of squared residuals, right? I changes from 1 to your sample size n, and minimizes the sum of squared residuals for every single beta hit. Beta hit 0, beta hit 1, beta hit 2, and so on, beta hit k. So guys, again, I'm not explaining anything new up until now because I have already explained all of this before. This is just a review to refresh our minds before we really proceed. So, and then you may have a question, where do we see these beta hits in this expression? All of these beta hits are hidden in U hat. Why? Because we know that, can you tell me what U hat is? So U hat is what? Yi minus Yi hat, right? But this is equal to Yi minus, what is Yi hat? Yi hat is the sum of what? Beta 0 hat plus beta 1 hat times x1i plus beta 2 hat times x2i plus, sorry, so on, plus beta hat beta k hat times x ki. So now you see where we have these beta hits. Okay, so before I said that if k is greater than or equal to 2, the analytical expressions of beta hit j, where j changes from 1 to k, are either very complicated or does not exist, or do not. Can you tell me how our model looks when k equals 2? No, I mean, I want to have k which is equal to 1. In this case, our model has the following form. Right? And this is our initial bivariate model. And then we do the OLS estimation. And we get beta hit 1, which is equal something to something, and beta hit 0, that is equal to something. Can you tell me what is it, what beta hit 1 equals to? That is covariance between y and x divided by variance of x. And beta hit 0, that is equal to y bar minus beta hit 1 times x bar, right? So these are a nice analytical, simple expressions for beta hit 1 and beta hit 0, right? But as I said, if k is equal to, k is equal to, is greater than equal to 2, the expressions become beta hit j become very complicated. Of course, we still run multivariate models. So the topic of this chapter is multivariate models, and those are done using matrix algebra. Using matrix notations. I very briefly told you I said a few words about this before, but we don't really cover this in this course. But in fact, matrix notation simplifies stuff very much, and we are able to obtain analytical expression for every beta. It's like this: p equals x prime x minus 1 times x prime y. But guys, this is all of these are matrices, right? So this is like bold letters. This here stands for, this is the inverse, minus 1. And this is transpose. This thing there stands for transpose. So this is really easy, but we don't really cover that in this course. And this B in fact is a column matrix that consists of beta 0, beta 1, beta 2, and so on, beta k. So this is k by 1 column matrix. Similarly, x and y are also matrices. Guys, up until now, how are we doing? Are we doing well? This is just a review, but still, if you have any questions, please stop me and I'll try to answer. I just need to know that you are here.
We are.
We are present.
We're here.
Thank you, guys. If you have any questions, let me know. So, okay, that's a review. Before, I also talked about omitted variable bias. I will not re-explain that from the very beginning. You can see the notes that I have already uploaded, and also you can watch the recording for this class if But actually, omitted variable bias is a really important problem if there is an omitted variable bias. So I will just remind you guys what that means. By the way, did you guys have any chance to take a look at this chapter or the notes for this chapter before today's class? So then, okay, so then let me remind you what we mean by omitted variable bias. Do you remember when does omitted variable bias occur? So first of all, when we have a model, right? So in a multivariate model that can have whatever number of independent variables. So those variables that are in your model, those variables are known as included independent variables. But also there are a lot of, there at least could be a lot of, at least some variables that are missing from the model because of various reasons. Can be because we don't have data, can be because we don't really know that those variables affect our dependent variables. So this means that there is always a possibility that we have an omitted variable that is excluded from our model. Can you tell me when does omitted variable bias take place? When, to rephrase my question, when is it problematic to omit a variable from the model? To omit an independent variable from the model?
When it's not equal to 0?
No, but is not equal to 0. Can you be more precise? What is it that is not equal to 0?
U.
U and you are close. So it looks like you remember something, which is great, but let me give you guys this final result for our simplified maybe. So let me give you this. Let me answer this way. When the, or it is better if you write if the omitted variable is not correlated with any of the included Sorry. Variables, then there's no variable bias. Okay, that's the answer here. But if the omitted variable is correlated with at least one of the included variables, then the omitted variable bias happen. And that's really problematic. So why do you think omitted variable bias is problematic? So what does it really mean? So we answered to the question, when does it happen? But what does it really mean? How do you understand? So we already answered to the question, when does omitted variable bias occur? But how do you understand omitted variable bias? What does it mean?
Can I try?
Sure, of course.
So if we omit a variable and it's not correlated to other variables, it's okay that we omit it.
Yes.
But if we analyze it and see that it is related, then it can kind of move our whole result because it should be included and it shouldn't be omitted.
So see, very nice. So the thing is, so we know that expectation of beta j conditional on all of our x's, right? x1i, x2i, and so on, xki, so expectation of beta hat j given all of our conditional on all of our x's, this should be beta j, right? This means what? That means that beta hat j is inverse. This expression means that beta hat j is an unbiased estimator of beta j. Am I clear? But under or if there is a variable that is correlated with one of our x's and is omitted from the model, in that case, omitting a variable, that is correlated with at least one of our one of our independent variables, then you can guess, right? Then what? Then the expectation of beta
Expectation won't be beta j.
will not be x exactly. It's not equal to beta j. So is it a problem?
Yes.
Yes. Why? Do you remember the requirements that this estimator should satisfy? I said it already in the beginning of today's class, right?
Unbiased, consistent, and efficient.
It should be. If one of these requirements is not satisfied, then our estimates are not good. They are not good estimates. Do you understand what I'm saying? How do we define a good estimator? An estimator is a good estimator if it satisfies all of these three requirements. Otherwise, it's not a good estimator. Do you guys understand what I'm saying? And omitted variable bias violates this unbiasedness assumption, right? And because of that, beta heads are not good estimators for true betas. That's all, guys. That's this is in words, but before I gave you guys a very simple formal derivation of this omitted variable bias, and please take a look at this, which is look at it in which is in our. I mean, I think if not the last class notes, maybe a class before that, because during the last class I think we had review for the midterm. Okay. Very good. Now, so the last parts that I want to okay, give me a moment. So, okay, let's talk about model fit. Let's now talk about model fit. Do you guys remember measures of model fit? One is R squared, and there is another, let me call this 3 because there is 2. And this 3 is what? Standard error of
Regression.
yes. And there is adjusted R squared. Okay, so do you guys remember the formula for R squared? Of course you do, right? So maybe not, but it's okay. R squared is what? That's
1 minus SSR over TSS.
okay. 1 minus SSR over TSS. This is exactly equal to what? TSS.
ESS.
Yes. So, and then this thing here, that is equal to ESS. Okay. So can you give me an expression for SSR? What is it?
The sum of yi minus yi hat squared.
Very good. Perfect. This is very good. So
Extra credit.
do you need it? I don't think you need it. So what is yi minus yi hat?
Variance.
No, no. Now I am subtracting points from you.
It's the sum of I equals 1 to n of
Guys, I'm asking a very simple question. What is yi minus yi head?
The error.
No, minus 1 point.
Oh, wow, okay. It's the residual.
Yes.
Same. Come on.
Guys, if you tell me that u is u head, or in other words, is a disturbance, if you cannot see the difference between disturbance and the residual, then I will reconsider your midterm. Square. I'm kidding, but guys, this is like very important. This is like these are basics, right? So that's the SSR, right? Okay. What is the SS? Can you tell me?
The sum of y hat minus y bar squared.
yi minus y hat.
Yeah. Wait.
Squared.
Yes. Oh, okay.
So if you interchange or substitute whatever, then it will not be ESS, right? So ESS is this. And how do we? What is this abbreviation? It stands for what? Plain sum of squares. And this stands for sum of squared residuals. Okay. And what is TSS?
The sum of yi minus y bar squared.
Very good.
That means total sum of squares.
That means total sum of squares. And R squared is a measure of it, which is calculated as ESS over TSS, right? Or in other words, that's 1 minus SSR over TSS, right? But one thing is to be considered. Now let me ask you, does higher R squared imply better fit? Can you tell me what do I mean by better fit?
If it's the correlation is high.
Now, can you tell me the intuition of this?
If the points are closer to the population line.
Okay, that's close. So, okay, so let's say we have this. So this is, let's say, our x1, this is, let's say, our x2, and let's say this is our y, okay? And then the points are all over this three-dimensional space. And let's say this is the true line, which is expectation of y, conditional on this is bold x, all of the x's. right? And that is equal to whatever. You guys know that, right? So beta 0 plus beta 1 x1 plus and so on plus beta k x. Sorry. Okay. In this case, that will be what? That will be just
X2.
right.
Yeah.
Okay, and then, but do we know this line? We don't know this line. And you're estimating that line, and that line, let's say, is maybe not. Let's say this, right? So this is what? Am I clear? Better fit means that these two lines are closer to each other. Do you understand what I mean?
Yes.
And the goal is to obtain a line, or in other words, to estimate a line which is closest to the true line. But the thing is, we don't know the true line, but still we have but still we can say with some certainty that our estimated line is closer to the truth. So higher R squared means that this estimated line is closer. Higher means closer to the true line. So, but okay, let me write it down. Higher R squared, I would say often means that the estimated line is closer to the true line. Why did I write here often? Can you tell me?
Because R squared equals 1 is a rarity, should be always look like we should always be skeptical of R squared equals 1.
Exactly, that's absolutely true. But it's not only about 1. If it is really close to 1, it's like if it is like 0.98, even 0.95, I would say R squared, which is I would say which is very high. I would say very close to 1. For example, 0.97, 0.96 or 99, then the fit is really very suspicious. Why? So which means what? Instead of a better fit, the model might be suffering by all kinds of issues, problems. Omitted variable bias, sample sampling issues, and so on, guys. One thing that we need to know is that if we add even an irrelevant variable to the model, R squared increases. So adding an irrelevant variable should not improve the model fit. Do you agree with this? So adding an irrelevant variable should not increase the model fit, but adding an irrelevant variable increases R squared. So we have a perception that we have a better model, but in fact we don't. So higher R squared sometimes can be misleading. Higher R squared can be obtained by adding an irrelevant variable to the model. So we need a correction for that. To correct for this, we use an adjustment. Okay? And the name of the adjusted measure of the model fit is the adjusted R squared. Sorry, guys. So the formula is this. So R squared is what, guys? 1 minus SSR over TSS, right? Adjusted R squared, this. One minus n minus 1 n minus k minus 1 times, and assume, so where n is the sample size and k is what? Number of independent, variables. And so therefore, what do you think is the adjustment here? This is the adjustment term. Guys, are you following?
Yes.
Yes.
Thank you, guys. So adjusted R squared is I would say an appropriate model fit. Now let me, the last measure of fit here is the standard error of the regression, and I will give you the formula for that for the multivariate model. That is do you remember what was our ACR? This is for multivariate model. And do you remember what was ACR for our bivariate model?
It was just 10 minus 2.
Very good. And that happens when k equals what?
1.
Right? Then do you agree with this? But when k equals 1, what is the model then?
Bivariate.
See? This is a general expression for the standard error of the model. And this is the special case. Of course, we will do exercises on these guys, so everything will be more clear. But hopefully we are not doing too bad. Now, the last part is the distributions of the OLS estimators for multivariate model. This will be a topic of the next class, but next week we will talk about the distributions of the OLS estimators. And work in Excel and R. That's the plan for the next week. Please try to attend classes. Do not miss classes if you can. I don't think I'll start a new chapter next week. I'll just give you guys more experience in working, more experience in working
With R?
with R, yes.
Yep.
I think that will be very useful for you guys. Also, I'll finish this. So that's all for today, guys, and I wish you a nice weekend. I'm happy that you did really well in the midterm. If you did not do that well, please don't worry because you can still improve in the final.
Thank you, Professor.
No problem.
Thank you, Professor. Have a good weekend.
You too, guys. Thank you very much.
Thank you.
Thank you, guys.
Thank you. Have a good weekend.
You too.
Extra credit.
The next homework.
Next homework will be assigned, I think, next week.
Thank you.
Maybe today. I'm not sure because there's like very small part that I want to explain in this chapter, and then I will assign. But I think I can assign the homework right now.
Yeah, can you do that so we can get a head start on it?
Yes, I will. I will.
Thank you so much.
No problem.